Alright, let's continue now our discussion, and we'll talk about the lubrication for the chain drives. Since it is, we can actually see that there are a lot of parts that's moving, even in the chain drive itself. There's a lot of parts that's moving relative to each other, so there's actually a need for lubrication. And even though it might look like it's a disadvantage of a chain drive, because if you compare that to a belt drive, they don't I mean the belt drive doesn't need lubrications, but this just simply depends upon the application. So there are advantages and disadvantages between the various power transmission elements. Okay, so there are a lot of parts that move, so we need to have a proper lubrication. Okay, so here's in our figure 11-13, there's actually a plot between the life hours of the chain drive and the wear in terms of percentage. Okay, so that means that if you have a life at this point, then you have a longer life, and if you have a life at this point, then you have a shorter life. And in terms of the wear, if you have at this level right here, then that's going to be a minimal wear, and you have much wear if you are in this range. Okay, so there are actually four, it's not that four, but rather that this one is taken from the manufacturer's catalogs. It's just superimposed with these labels. Okay, but the point right here, if we don't provide lubrication, then we'll have a chain drive that has this this lower life, okay, life in hours. Okay, so it will not last long, and simply the wear is just simply because there are a lot of wears, because there's a lot of frictions, and I don't know, it maybe wear and tear just simply because of the friction between the surfaces. But if we provide initial lubrications only, then we can increase the life, but again the wear is just basically the same. And if we provide intermittent lubrication, that means that we can extend the life even more. Okay, so it's right here. Now what if we have a sufficient lubrication all the time? So we can actually extend the life right here, and we can reduce the wear. Okay, so that's just the basic idea of why do we need lubrications. Just simply because we need to increase the life, extend the life and reduce the wear, so that we can have a maximum productivity during operations. Okay, so what lubricants do we need? Okay, so according to the PMC, that's the Philippine Mechanical Code 2008, is a good grade of non-detergent petroleum-based oil is recommended, and heavy oils and greases are generally too stiff to enter and fill the chain joints. Okay, so but according to this reference, a textbook by Robert Mott, there is a table depending upon the temperature range and the SAE number, okay, for the oils. That's the Society of Automotive Engineers. So these are the viscosity of the oil. So if we are having an operating condition of operating temperature of 38 to 49, then we'll use this SAE 40. If it's 5 to 38 degrees C, then we use SAE 30. Okay, so now for the types of lubrication. So how do we lubricate the chain drive? We have actually 4 types, or depending upon the reference, sometimes they just use 3 types. Okay, so the type 1 actually is just simply manual manual lubrication. So here it is. You just simply I mean, from the word itself, you can just apply the lubrication manually. So oil is applied manually by brush or spout can. So this is done once every 8 hours of operation. And for the type 2, we have a drip lubrication, and it looks like this. So here, if here's our chain, we have a 3 strands of chains right here, and we have here the lubrication. So it's just basically dripping to this to these portions right here, to this part of the chains. Okay, so that's a drip lubrication. And the another type is the bath and disc lubrication. So bath and disc lubrication. Here's the bath lubrication. Basically, it's an enclosed container or sealed container where either there's a bath I mean where there is an oil, and every time the chain passes through that through that liquid level or through that oil level, then it's being lubricated. Okay, so that's what we call the bath lubrication, and this is type B. So again, in our handouts we just use type 1, type 2, type 3, but in this reference they use type A, and it uses type B. But for the type B, it's either the bath or the disc or slinger lubrication, and still it is type B. Okay, and what else? The type C, or the last type of lubrication, is the oil stream lubrication, wherein it uses pump, okay, to deliver continuous stream of oil on the lower part of the chain. Okay, so it's a continuous lubrications. Okay, so that's all for the lubrication. Then how do we know which type of lubrication we will need? There's actually given in the manufacturer's catalogs, and even in our PAES, there's I mean, in the power rating tables, there's also a specification whether it's a type A lubrication or type B or type C. Although there are also charts, you might can find charts regarding the chain pitch and the speed, and then the proper lubrication. Okay, now let's move on to this design equations. Okay, when we compute for the average chain velocity, this is just something like the belt speed, the linear belt speed. This one is the average chain velocity, and take note of the word average. It's just simply because the pitch, or here, when this chain meets with the sprockets, it's not actually always it's not a perfect circle. Okay, so there is some fluctuations, and that fluctuation action is what we call the chordal action. Okay, so that's why we just use the term average chain velocity, and it's given by this equation: P times T times N. This is for pitch, chain pitch. This is the number of teeth, and this is the RPM, or the angular speed. Okay, so if we this 1000 is just simply the conversion of meters to mm. Okay, so we can what that means is that we can also have other units, like if we want feet per seconds or feet per minute. So we just have to do conversions. And now for the speed and teeth relation and speed ratio. Okay, so recall that in the belt drives we use the diameter, but right here for the chain drives you use the teeth, the number of teeth rather than the pitch diameter. Okay, so the basic equation is just simply N1T1 is equal to N2T2. Okay, so just this is the speed of the, let's say, the driver, and the number of teeth of the driving sprocket, and here is our driven sprockets. And for the speed ratio, it's just the end of the driver, or I think I have to check this if this is for the number of teeth, although it's also related. Okay, so let's move on to this chain length. Okay, so for the chain length, for simplicity, the chain length is calculated in terms of pitches. Here's our working equations. Take note of the form of this. It's something like the same as the bell tribes, except that this one is in terms of the teeth rather than the diameters. Okay, and so this length is, take note, L sub b. That means that's the length in pitch. Okay, that's the number of pitch. Okay, so L sub b, this is in pitch. It's a number of pitch. It's not the unit of length, but rather it's just the number of pitch. So if we want to solve for the chain length in terms of pitch, then our center distance right here, or the center distance, that's C sub b, that should also be in pitch, because sometimes this one is given in terms of unit of length, so you have to convert that length to the pitch. Okay, and it's just simply the pitch. If you recall this pitch, okay, so that's one pitch. And sometimes there is, in terms of dimensions, in terms of length, we have this let's say 12.7 mm per pitch. Okay, so if you have a pitch, let's say if you have a pitch in terms of the length right here, so if you multiply that to the length, I mean to this conversion, 12.7 mm for a particular type of roller chain, then you can get the unit of length right here, millimeters. Okay, so again, just take note of that. And right here, you would notice that there is a capital T and a lowercase t. Which is just, sometimes it's just more on the symbols, because this just means that for large T, it's the number of teeth for the larger sprocket, and this one is the number of teeth for the smaller sprocket. But you would notice that if you use the symbol T sub 1 and T sub 2, it's just the same as well, because it just simply means we are adding this, the driver and the driven, and right here in this term we subtract and we square, so we always get a positive number, so that doesn't matter as well if you use T sub 1 minus T sub 2. Okay, and we can also compute for the center distance, and there is an equation for the center distance. And what else? The pitch diameter of the sprocket. So what if we want to find the pitch diameter of the sprocket? So right here, here's the equation. So the pitch diameter is just simply the pitch divided by the sine of this 180 degrees divided by the number of teeth. Okay, and next thing is this angle of wrap. So the angle of wrap is just something like the arc of contact for the bell drives. Okay, but I think this is probably more precise, if I can say that, angle of wrap. So we compute this using this equation, and this is in degrees, because sometimes there's also equations in terms of radians, but just take notes of this. This is D sub 2 minus D sub 1. This is the pitch diameter divided by 2 times the center center distance. Okay, and the negative sign is for smaller sprocket, and the positive sign is for the larger sprocket. Okay, and the angle of wrap, just take note of this, that the smaller sprocket should be greater than 120 degrees. Okay, so for the design power and adjusted power, so here's our new term right here that we encountered. We didn't encounter this in the bell drives. What it says that the design power, we already know that's just simply the rated power, but this time this is more on required power of the machine. Okay, required power of the machine times the service factor. Okay, so service factor, again, we are going to refer to tables, right? Tables, and this M right here, this is what we call the multiple strand factor. Okay, and in our PAES and some references, this multiple strand factor appears at the denominator, but in some references I've found that this appears in the numerator. Okay, so I don't know why there's why is it like that, but we'll just use this M in the denominator because that's how it looks in our references, I mean in our PAES. Okay, so this multiple strand factor, basically that if you have a higher number of strands, then of course you have higher power. However, this is not a linear thing. So if you have a double strand, it doesn't mean that you have this, I mean you have a value of 2 right here. I guess let me show you this table. So here's in our PAES. So this is table 21, multiple strand factors. So if we have 2 strands, then we have a multiple strand factor of 1.7. This 3, then that's 2.5. This 4, then that's 3.3. And for the service factors is found in this table 20. And just take note of these conditions, like for example here it says type of driven load. Is it smooth, moderate shock, or heavy shock? Shock loads, like for example hammer mills, probably here, or combine harvesters. So if our source is an internal combustion engine with hydraulic drive, or an electric motor, or internal combustion engine with mechanical drive, so here's our factors, here's our service factors. Okay, and there is this adjusted power, although in our PAES it says power rating required, but for me I'll just use this piece of A, which means adjusted, because the basic idea is that this design power is multiplied to the design life and the service life. So here we have L sub D, right? L sub D, and L sub S. Okay, so for agricultural machines, the design life is just 5,000 hours, and this service life, this is always, or typically this is based on 15,000 hours. Okay, so that's why we do adjustments in this design power, so that you can accommodate here the difference between the service life and the design life. Okay, so 5,000 hours, that's for agricultural machines, right here. So you can just write, you can just read that information right here in 7.6.2 of our PAES. For agricultural machines, that's 5,000 hours. Now for other machines, you can find that actually it's a tabulated, or it's in tables, that if you have other equipments, then there's also a specified number of hours. Okay, then now we'll go on to the code provisions. So chain drive arrangements, so we can have short centers. So for short centers, the sag must be at the bottom. For long centers, the sag must be at the bottom as well, because imagine if you have if the sag portion is on top, then you can have excessive deflection, and that upper strand can hit these lower strands. And in terms of position, whether vertical or horizontal, for vertical, there's also specifications here regarding the position of the sag. And for horizontals, whether the sag is on top or at the bottom, that can work, again provided if that's a short centers, but preferably the sag should be at the bottom. Alright, so now let's move on to this center distance between sprockets. So how do we know how far do we space the sprockets apart? So it should be I think I should write it like this, because it says here 1.5 times the diameter of the largest sprocket. So let's write it 1.5D. Okay, so here's our C max. Should be, let me write it here. So sorry about that. C max should be the minimum of the two conditions. So the first condition is it must be 1.5 times the diameter of the largest sprocket, or the large it says, and not less than 30 times the pitch, nor more than 50 times the pitch. So it must be less than, sorry, it should be not less than, so therefore it should be greater than the 30 pitches, right? But must be less than, it must be less than the 50 pitches. I think this is how it looks like. So 1.5D, but it should not be less than this 30 pitch or more than this 50 pitch. However, a center distance equivalent to 80 pitches may be considered an approved maximum. Okay, so this is also specified, I guess, in the PMC. And also the chain should extend around 120 degrees, so that's the angle of wrap, and you can just read here. But for the minimum, of course, if we have a sprocket that's so close to each other, then there's going to be problems on the interference of the teeth. So that's why we have to also take that into account. Okay, so we can check that through this, but other reference uses this one. So that's just simply the diameter of the large sprocket plus the half of the diameter of the smaller sprocket. So that's the D, the capital D, and the lower D. Okay, and for the slack side, then you can just read it here. There must be adequate slack is about 4% of the span for normal tribes and 2% for these conditions right here. Okay, now for the design procedure. Again, as I've always said, that this design procedure is not something like an absolute, because that depends upon the design situations, the requirements, or the constraints. Okay, so usually what we do in our homework is we first obtain the necessary information, like the power requirement, the type of driven equipment, or the loads, or the lubrication, the shaft center distance, speeds between two shafts. So we obtain that. Once we obtain that, then we can start calculating the design power. And of course, in our case here for the chain drive, we will also use we'll also compute for the adjusted design power. Okay, and after that, if there are also other parameters that we can compute, then we will solve for that. Like for example, the angle of wrap or the pitch diameter. Okay, but for the chain and sprocket selection, then when we say chain selection, we must specify the roller chain number and the chain length. Because once you have the roller chain number, then you can actually have the size of the sprocket, and we only need to specify we only need to specify the number of teeth for the sprocket. Okay, and for the number of teeth, we'll just use this speed teeth relation. And for the chain length, just take note again, this center distance, this is center distance in pitch, then this one would be in pitch. And if we want to compute the length I mean in terms of the length units, then we just have to multiply that to the how many per pitch. Okay, and after that, then we also need to check other provisions and details, like for example we need to check the bore diameters, the center distance, what else, the sprocket tooth interference, and also other details. Okay, so that's very typical. And finally, we need to provide a design summary. Okay, so that's enough, and we'll now discuss the contents of this PAES. Okay, so for the chain drive systems, we have here the PAES 303, 2000, and you can just read the terminologies right here, but I'd like to discuss the tables. So for table 1, it's the table for standard roller chain dimensions. We have here the standard chain number. So if it is RC25, RC40, RC50, so what's the pitch? Okay, so if we want to convert the chain length or the center distance in terms of pitch to the unit of lengths, then we will need this table. Okay, so that's the standard roller chain dimensions. And what else? For table number 2, this is standard roller chain sprocket diameters. Just take note here, chain number 25. So if we have this number of teeth, then we can find the pitch diameter. We can also find the outside diameter, and right here another column. This is a continuation. If you have 43 to 75 teeth and 76 to 108. Okay, just take note, this is this is a standard roller chain sprocket diameters for chain number 25. And the next table is for 35. The next is 40, 50, 80, right? That's table 7. And until table 9, that's 120 mm. So that's the standard roller chain sprocket diameters. Okay, what else? Then for table 10, it says here the recommended roller chain sprocket maximum bore and hub dimensions. Okay, so that's the maximum bore and hub dimensions. We have to check this because sometimes it might not fit our shaft. Okay, so right here, that's the chain number 35, 40, 50, and here's the number of teeth. And the intersection, like for example the maximum bore or the maximum hub, if we want, then we can find this value. Okay, we have 100 chain number, 100, 120, 140 until 180. Okay, what else? Now starting from table 11. Table 11, that's the power ratings for standard single strand roller chain number 25. So this is table 11 to, I guess, table 19. That's just simply the power ratings of a single strand. So something like the power capacity of the chain per single strand. Okay, so what you will need here is, if you know the RPM of the small sprocket or the faster sprocket, you'll see right here, that's the RPM, and here's the power capacity, right? So our selection would be, how do we know the number of teeth? Like if we because we can compute for the required power through the design power equation. Okay, so if you have this 900, right, you know this is speed, and you go down here so you can get the number of teeth of that small sprocket. So once you have that, then you just apply the speed teeth relations to obtain the next, to obtain the other sprocket. Okay, so right here there is a portion for if it is a type A lubrication, type B, type C. So there is also a delineation right here. Okay, so any selection within this range, then that's type A. Any selection within this range, then that's going to be type B, and here type C. Okay, so that's for table 11 to table 19. You just see the number right here is just changing. This 35, and then later on we'll see the number 60, right? So you just have to check the proper tables. Okay, and finally we have this number 120, right? Okay, now for table 20, this is service factors. Table 21, this is the multiple strand factors. And here's our example, and we'll do this in the next video.